In this final video on the H8-16 card, I'm going to talk about kind of the documentation I've developed. We'll jump in and look at the machine again and come to the conclusion about the memory card. This should be the final video. Anyhow, as I've worked through understanding the H8, again, remember I came into this knowing nothing initially. I've developed this memory map that kind of shows the configuration of the machine as I have it. The blue areas here represent what I have in the machine that we'll see in the video after this segment. I don't have anything installed in the machine in this address space. Again, the addresses are defined over here. The PAM8 ROM starts at address 000000 and runs through address 003377. There's a data register that's mapped as a write-only location here at address 000001. If I had that card in, we could write to that address. I have nothing mapped in the machine from really this address 0400 through 037377. We'll look at that later in the video to prove that there's nothing actually there. I've then got the H8-16 card, the org address on it set to 040000, which puts the card's origin right here. And then if we go up to 16K, is this correct? 816, yeah, 16 plus H24K. I was thinking for a moment here, my math was wrong. We have a total of 16K of RAM starting at this address and ending at 137377. There was confusion, and we'll look at this a bit closer later in the video with what happens in this first block of bytes here in the RAM area, and this is really where the PAM8 monitor stores its flags and its working variables and that kind of stuff, so it's not meant to be user accessible. We then have the beginning of the user program space at 040.100. You see this when they have you hand key in programs like the memory test or the your H8 is up and running program. That way you're not writing over the top of the PAM8 storage space. When PAM8 wakes up, it walks through memory looking for the top of memory, and when it finds the maximum amount of memory you have, it sets the stack pointer on the 8080 CPU to that address. So the 8080 stack pointer is set up here at the top of RAM. They basically say they want to reserve 80 bytes decimal for the PAM stack. User programs could drive that stack even lower, potentially. So you've got the user program that enters here and grows up, and the stack space that really grows at the top of memory and grows down. If those two cross each other, you tend to crash the system. Anyhow, this is the documentation I developed. I'm not really sure why I have the bits set here in binary. I may remove that. That was done earlier just to aid me visually in working these out. I've indicated here that for ROMs, of course, read-only, there is that one write-only address to the H8-2. User RAM is read-write across the entire 16K space. So this has become my guide to understanding the configuration in the systems I have it. We can go in and look at the PAM8 control cells and flags. I've captured that information really here, and it just kind of goes through the things that I know about it. So of course there's the 040000 address at the beginning of the block. If you're going to dump memory to tape, you're going to put the low byte of the starting address in this byte and the high byte of the starting address here. There's other things that are labeled like in and out instruction, return. Again, a lot of these are used internally in PAM8 to control the system. The index of the register under display, so the the BC, DE, AF, PC, SP, etc. Period flag byte, I'm not sure what that is. The display mode, there's various modes you can put the front panel into with these display mode and user flags. You've got the starting at 040013, the front panel LED patterns. So the LED pattern that's on the, I believe, left-hand digit of the address space to the right-hand digit of the address space, and then left-hand of the data to the right-hand of the data. If you're dealing with loading tape, it calculates a CRC16 checksum that would be stored here. If there's a tape load error, it'll give you the error code here. Every time the interrupt on the system runs, it increments a counter. The least significant bit is sitting here at this address 033 and the most significant 034. So it's just a 16-bit up counter. When it counts to 16 bits, it'll count from 0 to 65,535 decimal. When it gets to 65,535, it just rolls over to 0. You've got a block starting at 037 that are the user interrupt vectors. So like if you've got a vector set up on a serial card that will trigger a jump to vector 3, the handler for that serial card's address would live here. And you get to the end of the block. There seems to be some bytes here at the end that are undefined, but PAM 8 basically reserves the space from 040000 so 3040077. And then, of course, the next address in the chain would be 040.100, which is, again, where the user programs begin. So this makes a lot of sense. I've done a lot of reading, a lot of going through manuals to be able to adjust this and finally actually make sense out of it. So anyhow, with this kind of explanation, let's jump onto the hardware and take a look. So let's go ahead and kind of prove the memory map I've developed is correct, and look at a couple of the oddities I saw in previous videos that I've been able to explain. So what I've got here is, again, the H8-16 RAM card. Its origin address is 040. So it should be occupying the 8K to 24K space. That agrees kind of with the memory map here. Hopefully this is coming into focus, where we have the PAM 8 ROM monitor in the lower 1K of space, and really a completely unused space up through 040000. That space has other ROMs and RAMs that could be inside of it for various cards. I don't have those cards in the system. So we can go in and look at some of this address space and basically prove there's nothing there. We'll go ahead and look in the space of 040000 through 040077, and that's where the PAM 8 control cells and flags live. It's also where the H8-16 RAM card starts. That card goes all the way up through 137377, which is the last address that card provides. The 8080 stack pointer is set to the top of memory that is found. So in this case, the PAM 8 stack will end up here. The PAM 8 stack will grow down as it's used. The PAM 8 stack wants 80 bytes, 80 bytes base 10 of storage dedicated to it. As a minimum. So basically this light blue right here becomes the user program space starting at 040100 coming across to over here, and the user program can live in this space, although if you got it all the way up tied against the stack area here, conceivably you'd crash. So a couple other things to note here. In an earlier video, the only way I could get the system to actually come up and run was with the H8-16 strapped at the origin address of 0. And that was quite confusing to me for some time, because I expected a memory map somewhat like I just described here, and this card to be able to occupy a higher address block. Let me pull the card out and talk about what's happened here. So in previous videos, I did some removal and movement of RAM chips to kind of discover better how this card's laid out. This set of chips was removed and put back in their original locations. Let's look at the drawing I did of the card to kind of explain this better. So this set of bank 3 RAMs were removed, put back in, and various experiments done. And then the bank 0, 1, and 2 were played with as well, and I'll describe how those were played with. So this bank 0, with the strapped to 040 as the origin, address 040 lives in this bank, and we work up through the top of the 16K address space. So with the original 3 sets of RAMs in these banks, the system wouldn't come up and run unless I set the origin to 0. And setting the origin to 0 had the effect of moving these 2 8K banks down to here and losing the rest of the RAM. In playing with the card earlier, I had removed this set of RAMs and then remove this set of RAMs and moved them down, and then remove this set of RAMs and moved them down to here, and move this set back up to the top. And now the card works as expected. What I really think has happened here is I had bad RAM down here in bank 0. Or possibly bad, well, probably bad RAM down here in bank 0. And that was affecting the PAM flags and variable space, causing the monitor to crash. And when I moved this bank down, I moved good RAM in. It's also possible, well, other things are possible. That's one working theory. But by shifting these two banks down and this bank up to here, it seems to have got the card into a space where it can be strapped as I expect it to be and actually run. So with that information, let's get this card back in the system. I commented on this earlier. It's much harder to get this card in when the camera's running. And there's a few things we'll observe here. So I've learned in reading about the... Oh, Rosie. Oh, Rosie. I've learned from reading about the PAM monitor that it wakes up with random garbage here on the screen. So this isn't telling me anything beyond its random noise. When the system comes up, it walks through the RAM space looking for the top of RAM. It's doing writes in various places until it detects the top of RAM and then sets the stack pointer there. So if we look at the stack pointer, we see that it's set to 137377. And if we go back to this address map, that 137377 where we'd expect the H8-16 card RAM space to end, with it strapped to live from 8K to 24K. So that makes sense. It's detected that card, all 16K on it, and set the stack pointer up there at the top. That stack pointer should then be living, I believe, in this upper bank here, bank 4, which would be that 20 to 24K space. Now I'm shuffling between various papers here. So we have our bank 0, 1, 2, and 3, and you need to add an 8K offset to these. But this bank 3 here, did I say 1 through 4? Bank 0, 1, 2, and 3. This bank 3 here is that last 4K bank of memory occupying the address space 20K to 24K. And the stack is then set to the top of it. You know, that's normally how a stack on the computer works, is you have a top of stack. And as you push stuff onto the stack, the memory addresses decrement, so it grows down. So this is now acting as I would expect it to. If we go look at address 000, so what we discover here is the ROM contents, and we saw this bit pattern before. That's the contents of the ROM. If I go to 001, actually that's the wrong place to go. What am I doing? If I go to 003377, that should be the last byte in the ROM, and I believe that's correct based on what I looked up and looking back through the ROM. When we roll over here to address 0400, this begins an unused address space on the machine. The bus is coming back with all zeros. If I try to alter this byte and put in, say, a 377, and step back, it's still 0. There's no RAM at that location. That unused address space runs all the way up through 040000. With option cards, there would be RAM and potentially, or ROM and potentially RAM in those spaces. We can prove that by going to address 0400 000, and we see RAM here. And if we step back, we suddenly see those all zeros again, saying there's really no memory there. And if I try to alter this address to 123, it stays zeros. So we've proven here that we have the PAM8 monitor in the lower 1K of RAM. We have no RAM in the system from the 2K to the end of the 7K space. Starting in the 8K space, or 040000, is the PAM control flags and registers, that kind of stuff. So if we move up through this, you may remember from an earlier video, this confused the heck out of me as I was walking through this memory space. Because we get up here to a certain address and we'd suddenly see this. We'd see noise, and I'm like, well, what is this? Although at some point I realized that looks pretty periodic. And if we continue up through, we'll find these spots here where I don't know if it's catching on camera. The data seems to shift a little bit when I come into address 22. Get to 23, it's all this weird walking stuff again. If we get back down to 040000 and look at what's actually in that memory, which is what I've written up here, is the PAM scratch area, flags, etc. So it starts at the 8K space. This byte, 000 and 001, would be where you'd enter the low and high byte of a tape dump start address. There's various things stored here. This is the index of the register under display, which I think was the program counter. There's a period flag, there's a display mode, there's user flag options that can be put in here to control how the front panel works, configuration bits, there's a bunch of refresh bits, and if we get to this bit 004 or 040012, it's this refresh index 0. And we can see that there's just stuff happening there. And that's just the PAM monitor doing its thing and using that RAM for, you know, who knows what. I'd have to analyze the PAM monitor deeper to really understand that. This address is 022 is the data register for what's being written in this byte right here, and that's kind of interesting. The addresses are staying the same, but it's the data 1 byte. So we have what I believe is the data 0 byte, the data 1 byte, and the data 2 byte. And those bytes represent the bit pattern that gets put on the displays here. So we can kind of prove this. If we go to, don't know if I can make this work or not. Let's go ahead and put in, let's go to address 013. Address is 013. And I'm going to change the value in this byte. And I don't know if you saw it. Did it do something or not? No, it's written the 201 back in, so the monitor is just overriding anything I'm trying to change. But those addresses represent the bit patterns. We have various other things here. Storage for the 16-bit CRC for tape. Tape error exits. If we go to that address 33, what we're seeing is the least significant bit of the system tick counter. So every interrupt, a 16-bit value is incremented, and this is the LSB value of that counter, and this is the most significant byte of that counter. And you can see it sitting here counting up as the system ticks occur. This counter counts from 0 decimal to 65,535 decimal, then rolls over. So it's just telling us the interrupt's firing, the monitor's doing its thing, and this tick counter is incrementing. Ooh, I just got a low battery warning on the phone here, so I'll have to hurry this piece up and get the phone charged. There's, let's see, we're at 035 is register content pointer, not sure what that is. 037 starts user interrupts. This is the jump to clock processor, jump to single step processor, and then if we get up to 45, this is the interrupt 3, 4, 5, etc. vectors. It looks to me like, looking at what I saw here, starting at 65, it's undefined, and in the ROM it can use bytes all the way up through 77. So as far as I can tell, these bytes are undefined. Don't know if they're actually being used. And then if we increment one more time, we fall over to that address 040100, and that's the beginning of the user address space. So if you remember the demo program we typed in, the memory test routine here is a good example. You set the base address to 040100, then start entering your program from this address on. That gets you right above that space for the PAM8 monitors, scratch and registers and flags, etc. So the oddities I saw earlier in this, where I didn't understand bytes that were changing on the fly, didn't understand why the card wouldn't strap at 040, etc., I think have been explained. So this said, I will stop this little segment, and we'll pick up in a second. So I've gone ahead and entered the memory test code from this section of the manual, which is, a set of bytes you go through. You've seen me do this before, and you enter the memory test program. And then at address 040105, you can put in the top memory limit. 057 for 4K, 077 for 8K is documented here. And looking at the source code from the memory test routine, I see no reason why you can't extend that byte to push the memory limits up. And in this case, entering 117 would end at 12K and 137 at 16K. So that should test the entire 16K card. If you look at this, and I don't know how well this is going to show up, the beginning address of the memory test is 040160, and basically that protects the memory test program itself. So you don't want to start testing on top of the program and crash the program. And if you look at the last address really here of the memory test, it looks like the last address occupied is 040144, which is interesting. That doesn't necessarily agree with the start. Yeah, it does. 040160 and 040144. Actually, 040154. 155 is actually the end. So what that does is start the memory test right above where we've entered the memory test into memory. And then this LXID of end is setting the final memory address. And this basically loops through, and it writes all zeros, and then 001 and 002, etc. to all those locations. So with the program entered, if we go up and look at address 5, we can see I've got the 137 in. The 137 is where I calculated the end of the 16K. For this RAM card, it'd be, and remember the RAM card is in RAM locations 040, 000 through 137, 377. So because they're stacking other stuff up here at the top, it won't test quite off the end of the memory either. So it's not testing the very beginning or end of the memory block. But we've told it to go through as close to the end of the memory block as it can. If we go in here and do a register PC, we want to alter it. We want to give it our starting address of 040100 and alter that. It'll start execution there. And then I want to watch the BC register here. And what will happen in this upper byte here is we'll see the test pattern that's being written. So if I run the memory test, you can see that it's walking through that 16K. And writing this bit pattern. We can halt this, and we're back at address 5. And just for comparison, I'm going to change this to 057 here, alter 057, which will tell it to test only through a 4K space. So let's go back and do a register PC oops. Register PC alter 040100. That's now set. Let's go ahead and monitor the BC, and what you'll see is this will increment really 4 times faster here when I run it. So this is just testing the first 4K on that card. I can halt that, and we can go back to memory address 5. We're going to alter that. We're going to set it back to the 137, so we test the full 16K of RAM. And there it is. Register, program counter, alter 040100, our beginning address that we're going to run from. We want to monitor the BC register and run. And this is testing that 16K of RAM on the card. Now this is ran for quite a while without detecting an error. So the question becomes, was this card really faulty when I started here? The machine wouldn't even come up with the card in originally without setting the base address to all zeros, which made no sense. And I think I even commented earlier then that that just made no sense to me, that I had to put the card at that base address of 0 based on the fact, let me find the memory map here, that the system really expects to start finding user RAM at 040100. And then it doesn't care if there's no RAM in this space here. We've got our 1K of ROM down here and then really nothing in this address space. It shouldn't care. And that's what I first surmised, and yet I had to map the memory starting down here at address 000000 as well, and that just didn't make any sense to me. And later on came to think that maybe I had bad memory in those first couple of 4K banks, and that by mapping the card down where bank 2 really become this space here, there was good memory and it could run. May have been the issue because when it was in the 16K space, here it would run. When I would push it up, it wouldn't. We swapped static RAMs, we moved them around, and eventually discovered that I could then put the origin of the board at 040 and have the system seem to run. And now it's running without memory errors. And early in I speculated that because these are single wipe sockets and the pins were rather dirty, that maybe this was just a bad electrical connection someplace in a socket. And I did a little bit of just kind of pop the IC up a little bit from the socket and reseat it. I didn't fully pull them out and push them back in. Maybe just the fact that I popped these fully out and moved, and back into the sockets was enough to reestablish what was a weak connection. I just don't know. The card runs through the memory test here. It seems, it just continues to loop. If there's a memory error, it'll stop and display the address of the error, and from that we could calculate which bank it was, and then we could go in manually and write various bit patterns in that bank through the keypad to determine what bit or bits were bad in that byte. So for whatever reason, random luck, mucking around here for several hours, we seem to have solved the memory issue on this H8-16 card. I guess I'm going to leave it at that, and I'll leave this keep running, and I will end this video here. So we'll talk soon.